Okay, so last time we were talking about inductors, and I said there's one more topic I want to talk about this semester, which is um, circuits that don't have a constant rate of flow of current. And I looked at my notes from last semester, and I didn't really get to this topic. Well, I got to this topic last semester, but it wasn't on last semester's final, which means I was in the same situation I am with you guys now, which is it's too important not to talk about, but it's too late to put it on the final. So I'm recording two more videos. One I'll post today, which is it's late Friday afternoon right now, and I'll post another one on Monday about some topics in electricity and magnetism that are just too important to ignore. So let's look at what we were talking about last time. Last time we were talking about the idea of an inductor, which is a circuit element that just looks like a coil of wire, and because any changing current in that coil will change the flux through that loop and cause an EMF due to Faraday's law in the opposite direction. Inductors resist any change in the current. Let's look at this a little more specifically. For example, we didn't write an equation for what inductors do or define the inductance very precisely. So let's do that right now. As you change the current through an inductor, the inductor creates an EMF in the opposite direction, proportional to the rate of change of the current. And we call that constant of proportionality the inductance. So the EMF is equal to minus L times di dt. If you want to know where we are in the book, we're in section 30-2. And that is a definition, which you will find in equation 30-5. So the units of inductance, if an EMF is measured in volts, and a rate of change of current over time is going to be amps per second. Okay, we define that unit a volt per amp per second is equal to, by definition, 1 Henry, which is not a unit of physics that you're going to see that often, but that's the unit of inductance. Okay, so the inductance is this constant proportionality between the rate of change of the current and the induced EMF, the induced back EMF that resists that change in current. We won't do any problem with just inductors. There's not a whole lot of point to that. What I do want to think about, though, is imagine you've got a circuit that has just two elements in it. A capacitor that is charged up with a certain amount of charge and has a capacitance C, and an inductor that has an inductance L. We want to think about what will happen in this circuit. So the capacitor is charged. A charged capacitor produces a voltage. The equation for that is the charge is equal to the capacitance times the voltage. That's going to want to push charges around this loop. If we're talking about the direction, the traditional current goes from positive to negative. So current is going to want to flow through that loop. The inductor, though, is going to want to push in the other direction with an EMF equal to the rate of change of that current. So we've got two circuit elements that are sort of fighting one another. The capacitor wants to push charge around the loop, and the inductor wants to resist that change in current. If we look at these two equations, they seem to involve different things. They involve the charge, and they involve the current. But remember that all current is equal to the rate of change of charge, the rate of change, the rate that charge is flowing past a point in the circuit. So if we combine these two equations, okay, the EMF generated by the capacitor is going to be equal to Q over C, where C is the capacitance of the capacitor. And the EMF in the opposite direction produced by the inductor is going to be equal to minus L dQ Well, di dt, but I is dq dt, so di dt is d squared q dt squared. We wind up with this equation that q over c equals minus L dq squared dt squared, or if we bring dq squared dt squared to one side, we have d squared q dt squared equals minus 1 over LC times q. Okay? The second derivative of the charge on the capacitor or flowing past some point in the circuit is equal to some constant with a negative sign in front of it times the charge. This is a differential equation that should look familiar to you. The rate of change of thing equals negative constant times thing. Okay? If we go back to the first few weeks of first semester, we looked at a situation where we've got a spring. Funnily enough, we draw a spring the same way we draw an inductor. And we say that we're going to use x to stand for the position of the spring, m to stand for the mass of the spring, and that the force produced by the spring is in the negative direction and is equal to some constant times the position. We can write F equals ma minus kx equals ma. And then we recognize here that acceleration is the rate of change of velocity, and velocity is the rate of change of position. So acceleration is the second derivative of position. So we can rewrite this expression, minus kx equals ma, as minus kx equals m times the second derivative of position, d squared x dt squared. And if we solve that, we can get something like d squared x dt squared equals minus k over m times x. And you should recognize that as the equation for simple harmonic motion. And the solution to this is that x as a function of t is some amplitude, a or x0, times the sine of omega t plus some phase angle. Or you can always set that phase angle to equal 0, so x equals x0 sine omega t, where omega is, remember, square root k over m. You need that square root so that when we take two derivatives of the sine function, we get that minus k over m out front. So simple harmonic motion is a differential equation that you guys should recognize, and it's a differential equation that, the sine function is always the answer you get whenever you've got a formula that says second derivative of thing equals negative constant times that thing. Well, look what we just got for this circuit with a capacitor and an inductor. The voltage is proportional to the charge, just like the force in a harmonic oscillator is proportional to the position. There is a resistance to a change in current, just like Newton's second law says there's a resistance to a change in velocity. And the result is a differential equation in Q. Okay? Q is our variable that changes over time. We've got one term that's proportional to Q, one term that's proportional to the second derivative of Q, and we get a second order differential equation that looks like second derivative of thing equals negative constant times thing. So we know that the solution to this is Q of t equals some initial charge times sine of omega t, where omega equals the square root of 1 over LC. I don't even have to do any calculus to solve this differential equation because it's an old friend that I recognize, and I should be able to just write down the solution to that differential equation, which means that what will happen in this circuit is if you charge up a capacitor and put an inductor in the circuit with it, that charge will start to flow, but the inductor will resist it and it will push in the opposite direction. It will push so much that the current starts to flow the other way, and the capacitor will fill up into the point where charge stops flowing, and then it'll start pushing the current in the other direction. It'll go like that, and the charge on the capacitor over time will vary sinusoidally, just like a mass on a spring starts to move in one direction. It moves in one direction until its inertia carries it too far, and the spring starts to pull it back, and it goes the other direction, and that goes forever and ever and ever. So an LC circuit, and we usually just abbreviate this, an LC circuit, a circuit with a inductor and a capacitor and nothing else, will result in a current that varies sinusoidally, and this variation will continue forever and ever and ever. Now, obviously, that doesn't really happen. Obviously, you can't just build a circuit with a capacitor and an inductor and charge it up and have that charge just flow around in a circle forever and ever and ever. Just like you don't really put a mass on a spring and let it vibrate, and that vibration goes forever and ever and ever. What really happens is there's friction or air resistance, and that sinusoidal motion gradually decreases. We call that damped harmonic motion, and we saw a differential equation for that as well, although we didn't spend as much time talking about it in first semester. The same thing happens in this circuit, because just like there's no such thing as a spring and a weight that don't have any friction or air resistance, there's no such thing as a wire that has no resistance. And resistance plays the role in one of these circuits that air resistance or friction plays in the idealized example of simple harmonic motion. So instead, in reality, any LC circuit is really an RLC circuit. A real circuit has resistance as well as capacitance and inductance. If you put a capacitor and an inductor in there, even if the resistance is small, there's still some resistance. So what does the differential equation look like for this circuit? This is called an RLC circuit. And again, if you want to follow along with the book, you will find this. The last example, section 30.6. This is the last section was 30.4. This is 30.5. This is 30.6. So this is 30.6, 30-6. They call this LC oscillations with resistance / LRC circuit. Well, before we said that the voltage created by the capacitor, if you were to charge this capacitor up, is governed by the equation that the charge on the capacitor is proportional to the capacitance, Q equals CV. The resisting EMF created by the inductor is equal to its inductance times the rate of change of the current. And the equation that governs the relationship between resistance and current is just V equals IR. Okay. So if we can think of this any way we want. We can think about it as just applying Kirchhoff's rule going around the loop. We go the wrong way across the capacitor, we go through a resistor, we go through an inductor. The differential equation we get is this voltage, which is Q over C, is equal to minus L di dt and minus I R. The minus, remember when you go across the resistor, you get a voltage drop. So the negative sign here is due to the fact that the inductor always resists the rate of change of the current. The negative sign here is because you always have a voltage drop when you go across a resistor. So if you put everything on the same side, and we make these substitutions, that I equals dq dt, right? Current is the rate of change of how much charge goes through some point. So that di dt equals d squared q dt squared, the rate of change of the rate of change of the charge. What we got here, let's put everything on the left side of the equation. So we've got L times di dt, which is d squared q dt squared, plus IR, which is R times dq dt, that's the current, plus I'm going to write this as 1 over the capacitance times Q. That's all equal to 0. Okay, so everything's on the left-hand side of the equation. All that's left on the right is 0. Let's... Oh, something is wrong here. Hold on a second. No, I think we're good. So I'm going to divide through by L. And what do I get? I get d squared q dt squared plus r over L dq dt plus 1 over LC q equals 0. That's the same equation for simple harmonic motion, okay, which would be this. It's hard for me to do that without putting a shadow. Okay. The second derivative term plus the constant term. If I put this on the other side, it'll be the same equation we had before. But with the addition of this term that's proportional to the rate of change. That is like in first semester when we had problems with if you've got a resistant force that's proportional to the velocity, that's like having air resistance in a free fall problem, or air resistance. You've got your mass on your spring, and you've got some force that's proportional to some constant times the velocity. I think we looked at a couple of problems like that before. So the solution to this is the same as the solution for damped harmonic motion. What the equation looks like depends on how big this coefficient is compared to this coefficient. Again, you can look at section 30-6 where they show the different mathematical relationships that'll produce the different results. But basically, if R over L is small and L over C is, or 1 over LC is big, you get what's called underdamped oscillations. You get an oscillation that looks like this. Okay. It starts out sinusoidal and it gets smaller and smaller and smaller. If this is much, much bigger, if there's a lot of resistance, okay, the energy gets dissipated by the resistor before the inductor can start to push back in the other direction. You get what's called overdamped, which does that. It just drops asymptotically to 0. And you can get in between, you can get something like this where it oscillates once and then asymptotically comes back to 0. Those are the different kinds of damped harmonic motion you can get. And it's exactly the same as the situation with a mass on a spring. So you've got this analogy between electrical harmonic motion in an LRC circuit and mechanical harmonic motion. What's the analogy? The thing that's changing in the electrical circuit is charge. The thing that's changing in a mass on a spring is, let me draw our pictures here so we know what we're talking about. We've got a capacitor, we've got a resistor, we've got an inductor. On this side we've got a mass on a spring with spring constant K. The thing that's changing in this is the position. The rate of change of charge, dq dt, is the current. The rate of change of position, dx dt, is the velocity. The rate of change of the current, we don't have a special name for that. Is d squared q dt squared. D squared x dt squared is what we call the acceleration. The thing that resists changes in velocity is the thing we call mass. And the equation F equals ma tells you how much resistance to acceleration there is for a particular amount of mass. The thing that resists changes in current is the inductance. So you can think of the inductor in an LRC circuit as being like the mass of that circuit. It is the bigger the inductance is, the slower the oscillation of the current will be. Just like the bigger the mass on a spring is, the slower the oscillation of the mass on the spring. If you've got air resistance, so that there's some force that's equal to minus beta times the velocity, that is like resistance. R resists current, air resistance resists velocity. Okay. So the analog here is that inductance is like mass, resistance is like air resistance, and capacitance is like force. It's like the spring constant. Q equals CV is analogous to force equals K X. Okay. So you can think of voltage as sort of the oomph or the push of either gravity or a spring. Remember, you can have simple harmonic motion with all sorts of objects. You can have it with a mass hanging from a string or whatever. So this analogy between alternating current circuits, RLC circuits, and simple harmonic motion is a really, really useful thing to know and understand. And your ability to see and recognize, I lost it, okay, see and recognize the differential equation for simple harmonic motion in a different context is really, really, really important. One of the sections we skipped in this, in our explorations of E and M, was way back in chapter 30. No, yeah, that's not what we want. Way back in chapter 26, and the capacitor. Chapter. There's a section 26-5, on what's called RC circuits. And we skipped it because we hadn't talked about circuits at all yet, and it seemed, or we hadn't talked about circuits enough yet, and it seemed premature to talk about circuits with changing current when we were just barely getting Kirchhoff's rules under our belt. If we imagine a circuit that's got a charged capacitor, let's say, and just a resistor. So you've got a capacitance with capacitance C, a resistor with resistance R. What will happen to the current in this little tiny circuit over time? Well, a capacitor is going to induce an EMF. The equation that governs that is that the charge on the capacitor is equal to the capacitance times the voltage, or the voltage generated by the capacitor is equal to the capacitance, or the charge divided by the capacitance. And this is going to want to push current around this circuit. If we use Kirchhoff's rules and go around the circuit, if we start here and go around this way, I'm going across a voltage minus, it's actually, I'm going from negative to positive, so it's actually minus Q over C is that voltage. And then I go minus IR is the EMF drop as I go across that resistor, and that's equal to 0. That just looks like an equation about charge and current until we realize that charge and current are related by the formula. Current is the rate of change of the charge. So we've got here is, I guess we can get rid of the negative sign. We've got 1 over c times the charge plus the resistance times dq dt equals 0. We put the derivative on one side. What we've got is dq dt equals minus 1 over rc times q. Okay? Make sure you can follow that algebra. This is the current. Put this over the sign. Divide through by, so this becomes negative, divide through by r. I've got 1 minus 1 over rc. That 1 is important. That negative 1 is important. It's important that we get the sign here correct. Because we should recognize this differential equation also. We've got the rate of change of something, in this case the charge, equals some negative constant times that thing. There's only one function that has that behavior, that its derivative is a negative constant times the thing, and that's the exponential function. So we should recognize that the solution to this will be something like the charge over time on that capacitor is going to empty out exponentially approaching 0. That Q is going to be equal to some initial charge times e to the minus 1 over RC times t. This is called the time constant of the circuit, and this section of your book goes through some detail talking about, well, doing some calculations of time constants for different circuits. I'm not really terribly interested in that part of it. If you're going to become an electrical engineer, you'll need to know about time constants of RC circuits. I'm more interested in our ability to recognize a differential equation that we have encountered before in a different context, where the thing changing is not the position of some object, but the thing changing is the charge in some circuit. And your book goes on and it does some more examples. Well, suppose you've got a capacitor and a resistor and also a battery in that circuit. What happens when you first turn the battery on? Well, the capacitor will charge up, and that will also be governed by an exponential equation. It'll look something like that. Actually looks very similar to the velocity over time when you've got an object experiencing free fall and approaching terminal velocity. But again, I'm not so interested in this specific application of this. What I'm interested in is the ability to recognize these things. I will say one thing, though, that is important about LRC circuits before I finish up. If you've got, well, let's just think of a mass on a string of length L, mass of m. We know that this will follow approximately simple harmonic motion. If you remember when we did the pendulum, you have to do a small angle approximation. It's only simple harmonic motion if the angle is small. It's actually only approximately simple harmonic motion if the angle is big. You know that if you've got a mass on a spring with spring constant K, that this thing will oscillate over time with some frequency that is determined by these physical constraints, m and k in the case of a mass on a spring, L and G in the case of a pendulum. The period of a pendulum is square root L over G. So the physical constants that describe the system determine the frequency of oscillation. If we've got a circuit that's got a capacitor and an inductor and a resistor, where the inductance plays the role of the mass. Oh, wrong thing. The capacitance plays the role of the force. The inductor plays the role of the mass, and the resistor plays the role of air resistance or friction. That the frequency of oscillation of this thing depends on these constants, particularly L and C. If R is small, then the frequency of this is approximately equal to square root of 1 over LC. Think about a mass on a spring, and think about someone sitting on a swing. if you want to push someone sitting on a swing, you have got to push at a particular frequency that resonates with the natural frequency of that system. You have to push them once every cycle in order to make them keep swinging and swing higher and higher and higher. Likewise, in an electrical circuit like this, if you want current to flow through this and keep going, you could push this with an external voltage, some kind of AC voltage, and the circuit will only oscillate with that frequency and not some others. In electronics, we can actually use inductors and capacitors and resistors to create circuits that have certain frequency properties. For example, think about, and a lot of these things are kind of obsolete now because we all use digital equipment to listen to music and to tune our car stereos. But think about an old stereo that has a tone knob, a bass knob, and a treble knob. Okay. Nowadays, if you've got a audio system with a bass and a treble knob, they're probably just telling a computer chip to do something with the frequencies. But in the old days, these were connected to electrical circuits that would either be a high-pass filter or a low-pass filter. And these circuits were tuned to only allow certain frequencies through the circuit. So what a treble knob physically did when you turned it is to change the resonant frequency of some combination of capacitors and inductors, such that if you have a bunch of different frequencies, low frequencies and really low frequencies and high frequencies and really high frequencies, it would preferentially kill the lower frequencies and enhance the upper frequencies, where the bass would do the opposite. It would preferentially not allow the high frequencies through and let the low frequencies. So I got this backwards, right? Yeah, the bass is a low pass filter that filters out the highs. The treble is a high pass filter that filters out the lows. Even something like the knob that tunes an old FM radio, where you select the frequency on the dial from 88.7 megahertz at the bottom all the way up to, I don't know what the top is, 107 point something megahertz at the top of the FM dial. And there was an actual physical thing that moved back and forth, and when you turn this knob, this actual physical thing would move back and forth on the face of the radio. What were you doing when you changed that tuner knob? Nowadays, again, you're just telling a digital circuit to do something different. But in the olden days, you were actually physically changing the capacitance of a capacitor in a circuit to change the resonant frequency of the circuit that picked up the electromagnetic waves from the antenna. If this is in your car has got an antenna that sticks up in the air. There's electromagnetic waves of all different frequencies impinging upon that antenna and causing the electrons in that antenna to move back and forth in all sorts of different ways. What the tuner does is it changes the capacitance in a circuit to only select out one of those particular frequencies to resonate with the electrons in the receiver and cause the electrons to move back and forth and send that signal to your speakers and make music. So when we tune a old-fashioned analog FM circuit, what you were doing is actually changing the capacitance, usually, of a variable capacitor. I'll see if I can find a picture of it, and I'll upload it to Canvas along with, or I'll put a link to it in the YouTube description so you can see what a variable capacitor looks like. Now, we haven't talked about electromagnetic waves yet. Electric and magnetic fields in the air that can oscillate and carry information from one place to another. And that's actually the topic of the last video. So that's all I'll say about LC circuits and RC circuits and LRC circuits. And on Monday, I will post a video about about electromagnetic waves and Maxwell's equations. So we'll have some sense of the history of the theory of electromagnetism and when we started to know that electromagnetic waves exist. And then we will be done for the semester. Check 1, 2. Good.